Vast, that is known by slope east shaping beneath it, soft music, slow rotation. You've probably imagined it, the launch, the countdown, the thunder, the triumphant roar as humanity punches a hole in gravity and climbs into the sky. And if you're like most people, you think that's the dangerous part. The fire, the explosion risk, the shaking. But here's the bold claim. The most violent part of spaceflight isn't launch. It's coming home. Reentry is not just a technical challenge. It's not just engineering. It is a direct confrontation with one of the most unforgiving facts of the universe. You cannot cheat thermodynamics. And if you try, the universe burns you alive, glowing like a meteor. Let's talk about why. When astronauts orbit Earth, they aren't floating because there's no gravity. They're falling continuously. They're moving sideways so fast that as they fall toward Earth, the Earth curves away beneath them. Orbit is controlled falling, but that controlled falling happens at about 28,000 kilometers per hour. Let me say that again. 28,000 kilometers per hour? That's not fast like a car. That's not fast like a jet. That's kinetic energy measured in nuclear weapon units. Fast, and here's the key idea. Re-entry isn't about heat. It's about energy. Vant, mv, described Ke on 1/2 mv12. The velocity term glows. Remember high school physics? Kinetic energy equals 1/2 mv squared. That squared part is everything. Double the speed and the energy quadruples. So when you're orbiting Earth, you're carrying an absolutely absurd amount of kinetic energy. It's invisible, silent, elegant, but it's there. And when you want to come home, you have to get rid of it, all of it. You can't land while moving at orbital speed, so the universe asks a simple question. Where does that energy go? It cannot vanish. The laws of physics say no. Here's where most people make a mistake. They think re-entry heat happens because you're rubbing against air. Friction. That's not quite right. It's more violent than that. Visual, molecules of air in the upper atmosphere. A spacecraft slams into them at hypersonic speed. At orbital speed, the spacecraft isn't gently sliding through air molecules. It's smashing into them. Imagine running through a room filled with ping pong balls. At walking speed, you barely notice them. At highway speed, they start to sting. At orbital speed, each air molecule hits you like a bullet. Not because it's heavy, but because relative velocity is everything. At the microscopic level, air is just molecules bouncing around randomly. They're not hot in the everyday sense. Temperature, fundamentally, is just the average kinetic energy of particles. Now imagine your spacecraft screaming into that gas. From the molecule's perspective, you are the meteor. You compress the air violently in front of you, and compression heats gas. That's not engineering. That's thermodynamics. When you squeeze gas quickly, you force molecules into a smaller space. They collide more often. Their average kinetic energy rises. Temperature skyrockets. Visual pump gets warm when you compress air. It's the same reason a bicycle pump gets warm when you compress air. It's the same reason diesel engines ignite fuel without a spark plug. Compression equals heat. Now scale that up. Instead of a bicycle pump, imagine compressing an entire wall of atmosphere at Mach 25. The air in front of the spacecraft can reach temperatures hotter than the surface of the sun. Not because space is hot, not because the atmosphere is evil, but because you are converting kinetic energy into thermal energy. The universe demands payment, and it takes it in heat. Here's the micro versus macro story. Microscopically, it's simple. Individual nitrogen and oxygen molecules collide elastically. They obey Newton's laws. They exchange momentum. Nothing dramatic. Just billiard balls bouncing. But macroscopically, you see plasma, you see ionized gas glowing white hot around the spacecraft. You see shockwaves, you see a fireball. Same laws, different scale. This is one of the most beautiful and terrifying aspects of physics. At the small scale, it's just particles obeying simple rules. At the large scale, it's apocalypse. Visual, split and splash, microscopic molecules, right side fiery re-entry plasma. Have you ever watched a meteor streak across the sky? That's not a star. That's a rock. Dying. And it dies for the same reason spacecraft would, if we didn't protect them. Because kinetic energy must go somewhere. Now, let's bring in something Richard Feynman would have loved to emphasize. Nature doesn't care about your intentions. You can't negotiate with entropy. Re-entry is fundamentally a story about entropy. You start with something incredibly ordered, a spacecraft moving coherently at high speed in one direction. That's low entropy, very structured energy. When you re-enter, That ordered motion gets scrambled into chaotic molecular motion. Heat, randomness. Entropy increases. The second law of thermodynamics isn't a suggestion. It's a one-way street. You don't get to say, I'd like my orbital kinetic energy to politely disappear. No, it must disperse. And dispersion looks like fire. So how do engineers survive this? Here's where the genius appears. Instead of fighting thermodynamics, they cooperate with it. Heat shields don't block heat the way a winter jacket blocks cold. That would be impossible at these temperatures. Instead, many heat shields are ablative. They sacrifice themselves. As they heat up, they chemically decompose. They char. They vaporize. And that phase change absorbs energy. Think about ice melting. When ice melts into water, it absorbs energy, but the temperature doesn't rise until the phase change is complete. That's latent heat. Now imagine a material designed to melt, burn, and peel away in a controlled way. It carries the heat away with it. It dies so the astronauts live. That's not poetic exaggeration. That's literally what happens. Let me give you another analogy. Imagine you're holding a stack of perfectly arranged dominoes. That's orbital kinetic energy, organized, directional. Now you knock them over. The ordered stack collapses into a scattered mess on the floor. That scattering is entropy increasing. Reentry is the universe knocking over your dominoes, except instead of wood blocks, it's molecular motion. Now you might say, why not just slow down gradually with rockets? Good question. You could fire engines to cancel out your orbital velocity. But think about the energy involved. To cancel orbital speed purely with fuel, you'd need an enormous amount of propellant, because rockets obey another unforgiving law, conservation of momentum. To slow down, you must throw mass in the opposite direction. And throwing enough mass to cancel orbital energy becomes wildly inefficient, so we use the atmosphere as a brake. But that means letting the atmosphere absorb that kinetic energy, and the atmosphere absorbs it violently. Simple solutions don't work because the scale of energy is enormous. You are not casually stepping off a bicycle, you are dissipating the energy of a small bomb. Biology doesn't save you. Hope doesn't save you. Only physics saves you. Let's zoom out for a moment. Why is reentry so violent, but orbit so peaceful? Up there, in orbit, you feel weightless, calm, quiet, because you're in a low entropy, highly ordered state of motion. It's elegant, but stability in orbit is a kind of illusion. You're like a coin spinning on a table. While it spins, it looks controlled, but eventually friction with the table slows it down, and when it slows down, it wobbles and collapses. Reentry is the wobble. Now here's the philosophical pivot. Have you noticed something strange? The same laws that make reentry deadly are the laws that make life possible. The second law of thermodynamics says entropy increases. Everything tends toward disorder. Stars burn out, planets cool, structures decay. And yet here we are, organized, thinking, building spacecraft. How? Because locally we can create order by exporting entropy elsewhere. Life is a tiny rebellion against disorder, but it always pays the price by increasing entropy in the environment. Your body stays organized by radiating heat. Civilization stays organized by burning fuel. Spacecraft survive reentry by dumping kinetic energy into the atmosphere. We survive by pushing disorder outward. The universe balances the books, always, and there's something profoundly humbling about that. When a spacecraft glows during reentry, you're witnessing a negotiation with the universe. Engineers aren't beating nature. They're respecting it. They calculate the trajectory precisely so the spacecraft hits the atmosphere at the core. Angle. Too shallow, you skip off and burn later. Too steep, you decelerate too violently and incinerate. There is a narrow corridor, a thin line between plasma and survival. That line is drawn by physics, not politics, not optimism. Physics. Have you ever wondered why astronauts describe reentry as both terrifying and beautiful? Outside the window, a roaring sheath of plasma. Communication blackout as ionized gas blocks radio waves. The spacecraft shaking. And yet, behind the shield, it works. Because someone understood molecules. Because someone respected entropy. Because someone trusted the laws of nature. Feynman once warned about something subtle. He warned that nature cannot be fooled. You can fool yourself. You can fool investors. You can fool politicians. But nature, she keeps the ledger. And re-entry is a reminder. If you miscalculate by a few degrees, if your heat shield fails, the universe doesn't negotiate. It converts your energy into heat completely. And yet, we keep doing it. We launch, we orbit, We come back through fire. Why? Because exploration itself is a defiance of stagnation. Not a defiance of physics, but a dance with it. There's something incredibly moving about a species that understands the equations governing its destruction and still chooses to ride the edge. When you watch a capsule streak across the sky, wrapped in plasma, remember this: you're not just watching engineering. You're watching thermodynamics unfold in real time. You're watching entropy increase. You're watching ordered motion dissolve into chaos. And from that chaos, a parachute deploys. A capsule splashes down. Humans step out. Alive. The most violent part of spaceflight isn't launch. It's coming home. Because coming home means surrendering energy, and surrendering energy in this universe is never G. Emtel. But maybe that's the deeper lesson. Every structure, every life, every orbit is temporary. We are patterns briefly holding back the tide of disorder. And the fact that we can understand this, that we can calculate the heating rate of plasma, that we can design materials to ablate just enough, that we can aim for a tiny corridor through chaos and survive. That's extraordinary. The laws of physics are not obstacles. They are the stage. Without them, there would be no stars, no chemistry, no life, no reentry fireballs, and no you. So let me ask you this. When you see a spacecraft burn across the sky, do you see danger? Or do you see the universe doing exactly what it has always done, transforming energy, increasing entropy, and briefly allowing a small thinking pattern of atoms to pass safely through the flames? Because the same laws that threaten us are the ones that made us possible, and maybe that's the most beautiful thing of all. We are not outside the universe. We are what the universe does when it understands thermodynamics. And every fiery re-entry is a reminder you don't escape physics. You participate in it. So the next time you watch a capsule come home wrapped in plasma, remember, it's not just surviving the most violent phase of spaceflight. It's proving that knowledge, real fundamental knowledge of nature's laws, lets fragile creatures navigate a universe that doesn't bend. And here's the question I'll leave you with. If we can ride through fire by understanding entropy, what other impossible barriers are just thermodynamics waiting to be respected? Let me know what you think.